In this video, we're going to talk about the pointing vector and how to use complex numbers, complex representations for electric and magnetic field to calculate the pointing vector. So you know that the expression for the pointing vector, which we're calling S, is 1 over mu naught E cross B. And that's generally true. That's a universal rule that has nothing to do with specifically optical frequencies or sinusoidally oscillating quantities. It's just always true. It's a direct consequence of Maxwell's equations and energy conservation. Now the issue comes up is that when we analyze electric and magnetic field and we write expressions for them, we typically write them as complex expressions. So that means that we're writing the electric field, we're usually writing that our electric field is the real of some complex expression. The problem, if we want to analyze a product, is that we want to know E cross B, which is the real of complex E crossed into the real of complex B. And however, that's not equal to the real of the two complex vectors crossed into each other. That's important. Let's look at an example just to make a quick example just to make sure we know about that. Let's just consider, forget about vectors, let's just consider two complex numbers A and B, where B doesn't mean magnetic field here, it's just the letter A and the letter B. So imagine complex number A is 3 plus 5i, and complex number B is 2 minus 4i. So if I wanted to know what A times B is, that would be the real of A times the real of B, complex numbers. And that, of course, the real of A is 3, the real of B is 2, and I would just get 6. However, if I look at the real of A tilde times B tilde, so if I take the product first and then take the real, I'm going to get a 3 times 2, which is a 6, but I'm also going to get a 5i times a minus 4i, which is minus 20i squared, or plus 20. There will also be some imaginary numbers in the product A tilde times B tilde, but when I take the real, they'll go away. But the 3 times 2 and the 5i times 4i, those will survive, and I get 26, which obviously is not the same thing as 6. So this clearly suggests that if I have an electric and magnetic field that are written as complex expressions, and I cannot simply write the pointing vector as the real of the product of those complex numbers. Let's get rid of this simple toy example. So now let's set up a real and an imaginary, a real and a complex way of attacking forming the pointing vector. So a real and a complex approach. So the real electric field as a function of time, the magnitude of it, might be that E of t at some location is E naught cosine of minus omega t plus some phase shift phi 1. And in the complex case, we would write complex E of t equals a magnitude E naught, and then we would use complex notation. E to the minus I omega t plus I phi. And then we would have the same thing for magnetic field. I'll just make that appear now. So there's the equivalent expressions for magnetic field. Now, if I form the product of E and B, now with optical fields, we're never interested in the instantaneous value of the pointing vector because things are fluctuating much faster than our eye or than the typical detector can make a measurement. So we're always looking at time averages. So the time average value of the pointing vector is what actually matters to us. So if we want to take the time average of E of t times B of t, this bracket indicates that we look at what the value of E times B is over time, and we just average that value. This is clearly going to be equal to the magnitudes times the product of these two cosine functions. So you could imagine taking the average of this expression, and you'd be multiplying two cosine functions by each other. If they were in phase with each other, this would just be cosine squared, and the average of cosine squared is a half. If these two functions are 90 degrees out of phase with each other, then cosine will be maximum when the other cosine is 0, then this cosine will go to 0, and this one will go to -1. And when two things are 90 degrees out of phase, the average goes to 0. And of course, if they're 180 degrees out of phase between phi 1 and phi 2, then this becomes negative cosine squared. And a negative cosine squared has an average of -1/2. So what are we going to do in the complex case? In the complex case, we have to analyze, strictly speaking, if we want to take this time average, we would have to take the time average of the real of E times the real of B. I haven't written the time dependence explicitly here, but this expression is exactly the same as this expression. We're literally replacing E of t with the real of E complex t. And that doesn't equal the real of E tilde times B tilde, which is the source of this problem. However, there's a nice theorem which says that in the particular case where you have e to the minus I omega t dependence on time, you can take this expression, and it happens to be writable in this case of this, when there's just sinusoidal time dependence, this time average takes on a very nice value. What you can say in this case is that that time average over here, this time average, is equal to 1/2 the real of E complex times B complex number, but the star means complex conjugate of that quantity. Notice what's nice about this expression here, it doesn't have a time average in it anymore. That comes from the fact that we know how each quantity varies in time. It just varies sinusoidally in time, e to the minus I omega t. And it turns out that time average then can be written as 1/2 the real of this product here, and then that can be written, let's just be explicit now. What are we taking the real of here? There's going to be an E0 and a B0. Those are actually real numbers, so we don't have to even put them inside of the real, but I'll leave them there. And then E0's, what's the rest of the E0 expression? It's e to the minus I omega t plus I phi 1. And then what's B's, the rest of B's expression is this. We have to take the complex conjugate of that. So we take all the i's and make them the opposite sign. So plus I omega t minus I phi 2. Now you see what's nice in here is that the e to the minus I omega t cancels the e to the plus I omega t. And so you're just left at the end here with 1/2 E0 B0 times the real of, all that's left is e to the plus I phi 1 and e to the minus I phi 2. So I can group the terms like that. And of course that's just equal to 1/2 E0 B0, and the real of this, real of e to the I something, is just cosine phi 1 minus phi 2. This is an interesting result. It captures some of what we were talking about before. If the cosines are in phase with each other, then this time average should be E0 B0 times the time average of cosine squared, which is 1/2. 1/2 E0 B0. Well, there's the 1/2 E0 B0, and if the oscillations are in phase with each other, this will be the cosine of 0 degrees, which is 1. So this goes to the right limit. What if the electric field and the magnetic field are 90 degrees out of phase? Then their time average should be 0. What do we get here? We get 1/2 E0 B0 times the cosine of, well, if they're 90 degrees out of phase, this is cosine of 90 degrees, and I'll get 0. So this expression seems to do the right job. We haven't proven this expression, but now you're seeing how it's used and how we happily are able to get around the time averaging problem of the pointing vector, still staying in our complex notation like this, making use of this nice theorem with just having to complex conjugate the b.